Hi, and welcome. My name's IreneLee, and I'm going to give a brief introduction to computational thinking. There is an urgent need to understand large, complex systems to address the problems that affect us all, such as climate change, loss of biodiversity, energy consumption, and the spread of virulent disease. At the same time, there's been a huge increase in computational power available to us through modern computers. These increases in computational power enable scientists to design and conduct experiments on models of systems that are too big, too expensive, or too dangerous to experiment with in the real world, to run multiple what-if scenarios, and collecting and analyzing large amounts of data. Fundamentally, computational thinking is a human ability to harness the power of computers to study and potentially solve real-world problems we are all facing. The definition of computational thinking as formulated by Jeanette Wing in 2006 is, computational thinking is the thought processes involved in formulating problems and their solutions so that the solutions are represented in a form that can be effectively carried out by an information processing agent. Later in 2011, the Computer Science Teachers Association and the International Society for Technology and Education developed an operational definition of computational thinking that sought to clarify what CT looked like when in use. They said it entailed formulating problems, logically organizing and analyzing data, representing data through abstractions such as models and simulation, automating solutions through algorithmic thinking, identifying, analyzing, and implementing possible solutions, and generalizing and transferring this problem-solving process to a wide variety of problems. Here's a rich example of computational thinking. So the problem at hand is we want to design a control system for a simple car simulation. We might formulate the problem like this. Our goal is to write a set of rules that allows a car to navigate roads using a computer to control it. So let's look at abstraction. One thing we abstract is what a road is. So in this case, a road is a surface that has a center stripe. What are the elements of the road that we take into account? It has a portion that's considered on the road, and there's an area that's off the road. Next, how do we describe a car being on the road? What does it mean to stay on the road? So let's look at what inputs our system could have. Let's say our car has a very simple sensor which can detect three states. The car is either on the road, to the left of the road, or to the right of the road. How do we design the rules for the car to follow? Let's start with the simplest possible design and prototype it to explore further. The simplest possible rule here might be to turn right when we find ourselves off-road to the left, or turn left when we find ourselves to be off-road to the right. Here's a simple algorithm that encodes this strategy. It says, at each step, move forward a little bit, and if to the left of the road, turn right by 2 degrees, and if on the right of the road, turn left by 2 degrees. This is called an algorithm. So let's review where we are so far. This is our model of a car traveling down a road. It contains an abstraction of the road and an idea of what it means for the car to stay on the road. It also contains rules for the car's behavior. Now we can run this model and see how it behaves over time. By changing the time slider, we can see if and how the car following these rules behaves. We can also add sliders to control the algorithm itself. We can then control the turn angle that the car uses when it is off-road, either to the left or right. But what if we want to understand the behavior of the system at every degree of turning between 0 and 10 degrees? We can abstract our algorithm. Now we see the word angle in place of the specific angle and see the representation of the paths created by the different angle settings. This is called sweeping a parameter. It produces data that can be analyzed to find patterns or the best solution. The purpose of abstraction is to bring out these high-level patterns. But are we done yet? We've abstracted over time, over the algorithm and data. Are we done? No, we aren't. Our goal is to design a good algorithm, and the algorithm we have is clearly not so good. But we've learned a lot of things. We've intentionally started with the simplest possible algorithm, and through exploring it, we understand why and how it is terrible. We've also learned several things. We have an understanding of the system. What are the possible outcomes? How does the system behave? We have hopefully some ideas on improving the algorithm, and we have an interactive visual toolkit and framework that lets us experiment. So, where was the rich CT? We saw abstraction. We represented the roads as paths. We simplified car behavior around 3 states. We developed the rules that dictate how the car behaves. We ran simulations that showed the passage of time. We used the computer as an engine to run our experiments. That's another way it used automation. And we collected and analyzed data produced by running the simulation to assess the outcomes, but also see the weaknesses of our model. So how does one develop as a computational thinker? We believe it involves gaining skills at formulating problems and designing solutions to make use of automation and abstraction. It involves learning to give instructions to a computer and learning how computers process instructions, and also learning about the computer's capabilities. We've seen that this is possible in K-12. During the NSF iTest program, we saw evidence that students were developing computational thinking in several types of projects, including modeling and simulation, robotics, and game design and development. To support the growth of computational thinking, we think that several things are important. Students should learn the capabilities of computing devices. We can provide opportunities to learn and practice basic computer science constructs and computer programming. We suggest using rich computational environments that allow students to look under the hood and see how it works. The use, modify, create progression has been seen to develop agency and deeper involvement in computational thinking over time. First, a student uses a base model and decodes it and explores what that model does and how it does it. Then, students can modify the model to reflect either local conditions or the questions that they're interested in asking. And over the course of multiple modifications, what was once someone else's becomes their own. In summary, computational thinking is the thought process involved in formulating problems and their solutions. A computational thinker uses the skills, habits, and approaches that are integral to solving problems using computers, developing models, and performing simulations. Thank you for listening. I hope this has given you a better basis for understanding computational thinking.